guys, today we're going to continue our journey in Unit 8, Acids and Bases. It's Part 4, and we're going to discuss how to calculate the pH of different acids, and we're going to start with strong acids. So calculating the pH of strong acid solutions. So let's just review something real quick. So HCl we know is a strong acid. So HCl itself is a molecule of hydrogen and chlorine bound together by a chemical bond. But when you dissolve it in water in the presence of H2O, then that hydrogen is going to fully separate itself from the chlorine, and the chlorine will be fully separate from the hydrogen. Remember, the hydrogen is going to lose its electrons to chlorine, so chlorine will be negative. Hydrogen is going to be that proton. And at this point, we don't have any HCl molecules left. That's what makes this a strong acid, that everything disassociates into hydrogen and chlorine on its own. Okay, so let's just keep that in mind for our later discussions. Let's also bring up a key term, which is the major species. The major species is going to be a really important step in figuring out the pH of a solution, of an acidic solution. So make sure you always think about the first thing, what are our major species in whatever solution you're talking about. So what is a major species? Well, if you look at the solution components present in relatively large amounts. Those are your major species, things you have a lot of. So for example, if you had 1.0 molar solution of HCl, then your major species would be, well, the HCl, you know, is going to break up into a hydrogen and a chlorine. So hydrogen ion, chlorine ion, and you're also going to have water. So these are your major species, the major things found in 1.0 molar HCl. Notice we don't have any OH minus, even though water ionizes itself and becomes H plus and OH, which is interesting. So you're like, oh, well, I've mentioned the H plus. But since this is a strong acid, and if you remember on the pH scale, right, if we're over here on the acids versus the bases, over here on the acid side, we have a bunch of H+. We don't have a lot of OH minus. OH minus would be if you're on the base side. So since we're over here, we won't have any OH minus that we can think of as far as our major species. So just keep that in mind. That's why that's not there. So if I wanted to calculate the pH of my 1.0 molar HCl solution, then I got to think about something. So think, who makes H plus? Because if you're calculating the pH, remember pH is the negative log of the concentration of H plus. So you got to wonder, where did that H plus come from and how much of it do I have from that thing? So I've got two things that could possibly give me H plus. I've got water as it self-ionizes, and I've got my HCl. So now I'm going to write out both equations just to kind of think through. So HCl aqueous is going to make H plus aqueous and Cl minus aqueous. Additionally, H2O goes back and forth between H plus aqueous and OH aqueous. So I can see that I've got two sources of H plus in my 1 molar HCl solution. So if I'm trying to figure out what the pH is, I have to figure out which of these is going to really give me the H plus. All right, so let's talk about our concentration of each of these if it were the only thing present. So like, if this one didn't exist, then this H plus would be in the concentration of 1.0 molar. Because remember, my HCl is fully disassociating. And because it's a balanced 1-to-1-to-1 chemical equation, whatever the molarity of this is the molarity of this, which is the molarity of that. So it's a 1-to-1-to-1 ratio there. So I know that my molarity of H plus from HCl is 1 molar. Also, we're going to assume that this is at 25 degrees Celsius, even though I didn't say it. Unless I give another temperature, or the AP exam, or any chemistry teacher gives another temperature, you always assume 25 degrees Celsius for any water dissociation situation. So we know that this is going to be 1.0 times 10 to the negative 7th molar, because we've memorized that, right? Remember, this is 1.0 times 10 to the negative 14, and that's the kW. So this is going to be the square root of that, so 1.0 times 10 to the negative 7. So if I compare these two, you can see, since this is 10 to the negative 7, this is a really small amount of H plus compared to this large amount of H plus of being 1 molar. So relatively, this is way more H plus. So this is going to be the dominant source of H plus. In fact, because there's so much H plus from the HCl compared to the water, that when water disassociates, it's actually going to act with Le Chatelier's principle, because we're adding a little bit more H plus. Most of the H plus is coming from here. So as soon as you add more, this is actually going to drive this bottom reaction to the left, because this is so much less than the HCl molarity, then Le Chatelier's principle is saying that this is extra stuff. So this will actually end up being less, a little less, and it'll push back towards the water. Because of that, we're not going to count this H plus towards the pH, because it basically, just as soon as it's made, it goes back, because you have so much H plus. So our pH in this one is going to comes from HCl. And it's because the concentration of H plus is so much higher in our HCl equation than it is from our water dissociation equation. So since I have so much H plus there relative to this is my source of H plus. This ends up just acting in Le Chatelier's principal actions, pushing backwards towards water, and not really being a thing. So our pH, therefore, is going to be the negative log of the concentration of hydrogen, which is going to come from here. So of 1.0. Our pH in this is going to be 0. Sig figs get a little weird with zeros because 0 technically has no sig fig. So if something's ever 0, you just put 0 and don't worry about it. There's a bunch of controversy of if that's really right. It's fine. That would not be assessed. All right. So let's do example 14.7, which I wrote out, and you have this in your supplemental notes. So calculate the pH of 0.10 molar nitric acid. And we know that nitric acid is a strong acid because it's one of the ones you memorized. And then after, we're going to calculate the pH of a different concentration of HCl. So let's start with part A. So remember, the first thing when I started is to do the major species. So if nitric acid is breaking up, it's a strong acid, so it's going to break up fully into H plus and NO3 minus. There won't be any HNO3 left. And then it's also going to have water. So I can write out my equations like I did before, or I can think about where is my H plus coming from. So I've got two sources of H plus. I'm just kind of shortening what we did before. I've got 0.10 molar from HNO3. And I've got 10 to the negative 7th molar from H2O. Again, I'm looking just at my concentration of H plus because pH deals with H plus. the one you need to know to figure out the pH, and if I'm calculating the pH, obviously I need to know that. All right, if I compare these two, this is talking if you want to put it in the same terms. This is 10 to the negative 1 molarity. With a decimal at the end to keep that 0 significant. So just to, if that helps you see which is bigger, we can tell that this is much bigger. So this is going to be much smaller. So that's not going to be your source. In fact, making this from water is going to drive the pushing of making more H2O. So this won't even, it'll end up being way, way, way less. So this is our source of H+. So our pH is therefore going to be negative log of 0.10. We know that this is 10 to the negative 1, so that 1 is going to be your answer, because the log is how many tens, all that whole thing. You can go back, logs are explained. This tells us how many sig figs, so this is going to be 1.00 is our pH. Okay. So I've got my sig figs here. This is magnitude, so this is our magnitude. These are your sig figs. Okay. Let's do part B. Calculate the pH of 1.0 times 10 to the negative 10th molar HCl. All right, so our major species. I've got H+, Cl-, and H2O. My H+ came from, I've got it from HCl, so I've got 1.0 times 10 to the negative 10th. This is from HCl. And I've got 1.0 times 10 to the negative 7th, and this is from H2O. I've written it a little differently. You can figure out however ways you want to write it to list everything to make sense for you. So I'm kind of doing it a few different ways in this note. So your way is, you know, if you get it right, that's great. You can set it up 1,000 different ways. So these are my H+ options. So if I look at my 10 exponent, I can see which one is bigger. And clearly the one from water is the bigger one in this one. I have such a small amount of HCl that that's not going to give me any large amount of H+, so it's not going to affect my pH. So if the pH is just coming from the concentration of hydrogen from water, and we're going to assume 25 degrees Celsius because we haven't been told anything else, we have to be told something else to assume a different temperature, then I know that this is going to give me my pH, so it's going to be a neutral pH, or a pH of 7.0. You could also do the negative log of this. This gives you your magnitude 7. These give you sig figs 0, 0. So here's your pH. All right, guys, you can now do number 8 in your worksheet packet. So go ahead and start that. There'll be another 2 videos today that you can check out. So we'll have part 5 and part 6. So you can start number 8, and then we'll move on.